Okay, this is class 5, concurrency. Let's go ahead and get started. All right, so quick review of what we did last class. We talked about locks. And if you remember, locks are kind of a simple synchronization mechanism with two primary operations. Acquire, which basically, if the lock isn't available, it blocks and waits there. And then release, which what release does, it releases the lock, and then something else that was blocked and waiting can then be unblocked and continue. So the idea is we would put a critical section of some sort in here, something we want to have mutually exclusive access to, enforce mutual exclusion on. So as we come down here, we hit the acquire. If somebody else is already in there and has it locked, then we won't be allowed to proceed. The only way we will proceed is if that lock is then released, and then we can acquire it, and only one thread at a time can ever acquire to proceed into the critical section. And a quick review of how we did that in Python. We basically make a lock object using threading.lock, and then we do mylock.acquire, or acquire that lock, have the critical section, and then we have the release. There was an alternate way to do that using a with block. So we say with mylock, and then have the critical section code indented underneath that. And then that will automatically acquire it. If we get into here, it'll release it when we exit that indented block. And this is considered a little more structured because we can't accidentally acquire and forget to release. So, but this is a little more explicit, so we can see when it's acquired, we can see when it's released. To be honest, when I write code, I usually do the explicit acquire and release. Although this is considered a little more structured, it could just be, that's what I'm used to. But you could do it either way. And the second one is, I guess, considered preferred, but either way. All right, a couple more things with locks before we move on to what we're going to talk about today. And that is, there are a couple of additional optional parameters that you can use for acquire. And those are, and notice I have the defaults listed here. So blocking, you can say equal true as the default, but you could also say blocking equal false. And if blocking is set to false, essentially the acquire won't block. It won't stop and wait. It'll return to us true if the lock is acquired. It'll return to us false if it can't be acquired. So in other words, this is a way to kind of say, hey, I want that lock, and be told it's not available by this acquire returning false. But if we do that, it's up to us to then say, hey, if it wasn't available, don't enter the critical section. Maybe try again later. But it's also a way to make sure that if we try to acquire the lock and it's not available, we don't just lock up our program. So it allows our program to maybe do some other stuff for a while and then come back and try to acquire it again later. There's a second optional parameter for acquire that's timeout. And if the timeout is set to -1, it'll block indefinitely, just like normal behavior. But a positive floating point value will indicate that a number of seconds, we should wait for a number of seconds while blocked and waiting for a lock. And it'll then either time out and return false, or it'll acquire the lock and return true, and then we can continue on into that critical section. So this is a way to say wait, but don't wait forever. Wait for some amount of time. If we put 1 there, wait for 1 second, and then time out. But no matter what, the return value from this is always going to be true if we acquired the lock. It's always going to be a false if we didn't. And if we just use the defaults here, true and -1, or don't even put these in and just say acquire, it'll block indefinitely, and it will block, and the only way we'll proceed is if we have acquired the lock. So then, again, the reason for those is to create code that won't block forever waiting to acquire a lock, to give us the ability to have that thread maybe do something else, or do something else if it couldn't acquire the lock in a certain amount of time, to have some sort of fallback plan rather than just locking up and sitting there forever. Now, there's one other type of lock that I want to talk about, and that's called an RLock. And those are called RLock. The R stands for reentrant. So those are reentrant locks. And they work just like locks, meaning they have acquire, they have release. If we acquire and we are granted the lock, then that allows us in. But there's a couple differences in how those work and how the standard locks work. And essentially what an RLock does is it locks out every other thread except the thread that we're in to be blocked out while we have acquired the locks. In other words, the same thread can actually acquire that lock multiple times. And the other threads that try to acquire that lock will block on an acquire, but our one, if we hit acquire more than once, then it's okay. We can hit acquire once, we can hit acquire again, and it won't block. We can hit acquire again, it won't block, but if another thread hits acquire, it will. And so for every, there needs to be a release function called, a release method called on that lock for every time an acquire was called to return the lock to being in the available state. And the main use of that is to make something that's recursive. In other words, you have a function that while it's running, you want it to lock everything else out, but part of that is that it has to call itself. So if it's going to call itself, it's going to hit an acquire again, and then it's going to call itself and hit an acquire again. We want to have the recursion unwind all the way. So if you were, for example, making a recursive, I don't know, sorting algorithm like quicksort, and it calls itself and calls itself and calls itself, but while you're sorting the data, you want everybody else to be locked out, you could implement that with a recursive lock. A normal lock, if it's locked and that same thread tries to lock it again, the same one will block, but a recursive lock allows the same thread to acquire it multiple times as long as it's released the same number of multiple times. All right, so note that in all cases for both locks and recursive locks, the thread that acquired the lock must also be the one that releases it. So in the case of a lock, one release. In case of recursive locks or RLocks, let's say 5 acquires, 5 releases are required. But it always has to be the same thread. In other words, if a thread locks a lock, it has to be the one that unlocks it. Another thread can't just say, hey, I'm going to unlock the lock that you locked. In other words, a thread cannot release a lock that was acquired by a different thread. It has to be the same one. And that makes them perfect for protecting critical sections, that you don't want another thread to be able to unlock your lock. So think of it like a porta potty. You want to be able to go into that, lock the door. The only person that can unlock the door and for you when you come out of the porta potty is you. You don't want to have it so somebody else can walk up and say, hey, I see that door's locked. I'm just going to unlock it and kind of traipse in there. And now we don't have mutual exclusion anymore. So that makes them perfect for mutual exclusion. And again, it's a simple form of thread synchronization to lock the lock. You do what you need to do. Every other thread that's trying to access that critical section is kept out. And when we're done, we unlock it. The other ones can now, one of the other ones can proceed and acquire the lock. Now, that restriction on requiring the thread that locked it to also be the one that unlocks it, while it's perfect for protecting critical sections or guaranteeing mutually exclusive access to some resource, it can also create an issue where there are certain situations where we need synchronization, but we need it to not be like that. So let's take a look at one of those. So one of those, the one that we're going to talk about today, is called producers and consumers, or a producer-consumer relationship. So imagine we have 2 threads, one that's producing some thing, another one that's running concurrent with that that's consuming that thing. So imagine this is like you think of this like a factory where this is producing a car. Here's the car. This is then consuming the car and painting it or whatever, and then going on. Or maybe you think of this as a computer system. The producer thread would be like the thing reading your key presses as you're typing on the keyboard. They're going into this thing that's holding the last key press, and then the consumer is the operating system or program that's pulling the key presses out of this buffer that sits between them. So a producer is producing data, consumer is taking the data that the producer produced and doing something with it. And there could be a lot of cases like that in a program. Could be a thread that's reading data from the hard drive and making it available for a program that wants to read that data, a buffer sitting between. So first off, consider a single cell buffer, a single item buffer. So in other words, the consumer can't take an item until it's been produced. And think of the producer. If something's already in this slot and hasn't been consumed yet, the producer can't produce another one because it'll overwrite the one that was there before. So let's say we type A, B, C, D. If we try to consume before there's something in the slot, A hasn't even been pressed yet, so we'll get whatever garbage data was in there. Or if producer, if I A and B, I put A in there and I put B in there, but consumer hasn't taken A, then the A disappears and I overwrite it. So the idea here is we want to have it so the consumer can't take an item until it's been produced. And we also want to make it so the producer can't place another item in that buffer, in that slot, until the consumer consumes the previous one. And even if we made the buffer a little bit bigger, like rather than just one cell, like we had in that case, the single item buffer, if we made it a 10 item buffer, eventually we would produce 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 items in the buffer. Now it's full. We can't produce another one until consume has pulled one out of that buffer until it's no longer full. So when that buffer gets empty, the consumer has to wait. So when the buffer fills up, producer has to wait. Consumer can then pull those things out, and then once that buffer is empty, then the consumer has to wait. So in that case, notice we have two different threads, one that's putting things into the buffer, one that's pulling them out of the buffer. And that means that a couple things. First off, the formal way of looking at this is for all valid executions, it's true that the produce sub I has to come before consume of item I. So in other words, if I produce the A, I have to produce it before it can be consumed. Makes sense. I can't consume something that hasn't been produced. I have to wait for this to complete before I can consume. And also, in this case with that one item buffer, I have to consume the one from step I before the one produce of the next step. I plus 1 can happen. Otherwise, we'd overwrite something and we'd lose data. So notice that requires a different kind of synchronization than we could achieve with lock or RLock. And in this case, notice that the producer thread only locks when an item is placed. And the consumer thread is unlocking that when an item is taken. And that's not something we can do with locks because they have to be locked and unlocked by the same thread. So in this case, we want the producer to put an item in and lock, and we want the consumer to take the item out and unlock it so the producer can put another one in. And we might, if we had a buffer here, we would only need to lock once this fills up, and then we would lock, and then as soon as this takes something out, it would unlock that. Okay, so to solve that, we need a different kind of synchronization mechanism. We need a synchronization mechanism that can be locked by one thread, but unlocked by another. And we want a synchronization mechanism also that optionally can count a certain number of items before locking, and then count backwards down to 0 as those things are consumed. So lock and RLock objects can't do it because it has that restriction on it has to be the same thread that unlocks it as the one that locked it. So we need something different. And that brings us to this concept of an object type called semaphores. Now they're going to look sort of like locks in the way that we use them, but they have a couple distinct differences. So semaphores were invented by a Dutch computer scientist, a very famous computer scientist named Edsgaard Dijkstra. And Dijkstra, you might see his name in a lot of things. He's got algorithms that you might see in artificial intelligence. He's got a lot of work he did in concurrency. He also did stuff with programming languages and programming language design. Notoriously, he detested the goto statement that are used in languages like BASIC. But a very pioneering computer scientist, and it did a lot of stuff in concurrency. So he invented this concept of what's called a semaphore. And semaphore, if you don't know, the name semaphore itself is a name for like a flag. And there's a whole international semaphore code where you hold up these flags and you do different patterns to make different letters. And that semaphore code is kind of where he got the idea for semaphores, the idea of being like a flag. But the way he thought of it was semaphores are kind of like they're a data type. So a semaphore is a data type like an integer or a float or a string or something like that. A semaphore is this data type. And just like any data type, it's got a set of permissible values and a set of permissible operations that can be performed on that data type. And sometimes it's useful to classify this as two different types of semaphores or classifications of semaphores, binary semaphores, and what are called general semaphores or counting semaphores. And we'll talk about the distinction between these here in a second. But the idea is that it's a data type, there's a set of values we can assign to them, and a set of operations we can perform on them. And let's look at the operations. So semaphores have the following operations. One is we can initialize them with some value of one of the set values. We can then have operation P, which in Dutch is proberen, which essentially stands for to test that. But we can think of it as wait or acquire also. So these are all kind of English words that maybe are a little more familiar to you than proberen. But this is what Dijkstra called it because he was Dutch. So he called it the operation P, proberen. And then the other operation is V, which stands for verhogen, which is essentially to release or signal. So you can think of this like probe and verify or something like that. But the idea here is acquire and release. Notice those are the same words we used for locks. So these have the equivalent of a lock dot acquire and a lock dot release, but they work a little bit differently. And these are the only operations that are permitted. You can create the semaphore and initialize it to a value. You can acquire, you can release. That's it. Similar to locks, but they work a little bit differently. All right, so to see how they're different, let's take a little bit closer look at what the operations actually do. What do P and V actually do? Okay, so P, which is the equivalent of acquire, basically it says, hey, if the value of the semaphore is greater than 0, then subtract 1 from it and then continue on our merry way. That's it. So in other words, if the value is greater than 0, decrement it. But if the value is at 0, we don't decrement it. We basically block and wait on that semaphore S. We wait on its value to become something other than 0. So in other words, if we hit acquire and there's a semaphore value available, it's greater than 0. Let's say there's 1 there. There's 1 available. We decrement to 0 and go on our way. And now V on release, what we do is when we hit this, we say, hey, if some process is blocked on S, on semaphore S, there's somebody waiting for this, then I'm going to unblock one of them. Otherwise, I'm going to put it back. So think again like this as a key at a gas station for the restroom. Basically, acquire is, hey, if there's a key available, take one of the keys, subtract 1 from how many are available. If there's not a key available, then I stop here and I wait for a key to be available. So I wait for a key. I fall asleep on the floor where the keys go. Now on release, when I come back from using that key, I basically say, hey, if somebody's waiting for the key, I give it directly to them. Here's the key. If there's nobody waiting, then I put the key back on the hook. Now, a couple things about that both P and V operations, all operations have to be indivisible, meaning they themselves are kind of like a critical section. In other words, I couldn't have 2 of them check at the same time and then 2 of them subtract at the same time. This has to be done in an indivisible, atomic, or mutually exclusive relative to all other operations of that semaphore. In other words, P has to completely start and finish before we could ever call V, or V has to completely start and finish before P, or P1 has to completely start and finish before the next one, the next acquire happens, or V1 has to completely stop. So in other words, these 2 things are not allowed to overlap each other for that particular semaphore. In other words, the operations have to be atomic. When we call P, it has to start and finish, except for the case of blocking. Blocking counts as no longer waiting. with respect to all other operations on that semaphore. Okay. One thing that is different from locks is the operations don't need to be in the same thread. We could acquire in one thread. We could release in another. That's allowed. It's not allowed in locks or RLocks, but it is allowed in semaphores. Now, to implement the semaphore types, basically we have binary semaphores. Their range of values are just 0 and 1. In other words, there's only one thing available. We call P, it goes to 0. We call V, it goes back to 1 or gives it to whoever is waiting. With counting semaphores, you can have 0 through n, so some number of values that are permissible. And that's useful for buffers with a set or some set number of resources. Like let's say you have a system that allows 5 concurrent users. So 5 concurrent users, you'd have a set of values 0 through 5. And as somebody logs in, it calls the semaphore for acquire, it goes to 4. Somebody else logs in, it goes to 3. Somebody else logs in, it goes to 2, and then to 1, and then to 0. And now that there are 5 concurrent users logged in, the next person, the 6th person, tries to acquire that. It's 0, so they block and they have to wait. And notice that other than those, the difference in possible values, that's it. The operators work the same for both binary and counting semaphores. So really, all semaphores could be just be thought of as counting semaphores, where a binary semaphore is one that's counting that only counts up to 1. But they work the same way. All right, so in Python, it turns out that the threading module has semaphore capability. There's a semaphore class built into it that we can use to make objects from. And notice it looks a lot like that. We do threading.semaphore instead of threading.lock. The only difference here is we can specify an initial value. If I leave that off, the initial value is 1. So in other words, if I leave off what kind of semaphore it is, it devolves to a binary one. It creates a binary one by default. But I could also put an initial value there, like 5 or 10 or however many I want, before it will block. And then you'll notice the way that we acquire and release, we don't use P and V. We use the same acquire that we used for lock, the same kind of release thing we used for locks. So the only real difference between this and locks is the ability to specify an initial value, and we use semaphore here rather than lock. And notice, just like with locks, the acquire method also supports defaults of turning off blocking and setting a timeout. So you could do those as well, and it works the same way as it does for locks. So the main difference here, the main distinction that I want you to be aware of is, number one, we don't have to acquire and release in the same thread. We could have those split across 2 different threads. And the second takeaway from this, besides it could do that in different threads, is that you can have this value associated with that semaphore. Locks are either acquired or not. Semaphores can be have a value. They lock when they are acquired completely when it gets to 0. But if it's greater than 0, there's some available. Now, Python also supports what's called bounded semaphore. And they work exactly like semaphores with one exception. And that is that when you create that initial value for a bounded semaphore, when we create it, the bounded semaphore, that's the maximum it could ever be. You could never have that have more resources than that maximum. And the main advantage of that is to help with bugs where you maybe release a semaphore too many times accidentally. So let's say we had our 5 concurrent users. You don't want to have somebody accidentally write bad code that releases and then releases again. And then we have 7 when there should only be 5. Or maybe you would think of it as like tickets to a show. The venue's big enough to fit 50 people. You don't want to sell more than 50 tickets. All right, so that takes us to lab 3. And this is a relatively short lecture today. And I'm going to give you some time to take a look at that lab and actually work on it today. And make sure you finish up lab 2. I'm going to pause this for a second and switch over and bring up the lab sheet so we can take a look at it. So give me just a second. Okay, so for lab 3, you're going to be implementing that producer-consumer interaction. One thread will be the producer, another thread will be the consumer. You're going to run that and observe the behavior, and then you're going to add semaphores to synchronize those threads. So let's go ahead and take a look at the lab sheet for that. So let me switch over the camera here. Okay. So in looking at that, you'll notice that essentially you're going to create 2 threads: producer, consumer. So this function is going to produce integers 1 through 100. So the first integer this will produce will be 1, and then it will go to 2, and then it will go to 3. And it's going to store those in a shared variable called buffer. So in other words, inside of here you'll have a for loop for I in range go 1 through 100, and you're going to say buffer equal and then I, or whatever the value is. And then after each number is produced, the program will sleep for a little bit and make it a random range. So random.uniform is good at generating these random ranges, but make it sleep for a random amount of time between 1,000th of a second and 100th of a second. So a pretty small amount of time. And once all of the numbers have been produced, in other words, once you've produced all 100 numbers, then you're going to print producer done. So that's producing them, and it's sticking them into that shared variable buffer. So if we were to watch the value of buffer as this runs, and this buffer is going to be a global variable, so you'll have to make those a global variable. Again, how to make that a global variable inside the function. If you're not familiar with Python, put the word global and then buffer inside of the function indented underneath that, and that will make it a global. It'll have to be declared outside of that as well. Global equals 0 at the start. But anyway, once that's done, you print out producer done. Now on the consumer, what it's going to do is it's going to retrieve the value that's in that shared variable buffer. So in other words, it'll say temp equal buffer or whatever. And we're going to repeat this 100 times as well. So another for loop that goes through 100 times, read the variable buffer, and then print it out. And then after you print it out, then I want that to sleep for 1,000th to 100th of a second as well. And once 100 numbers have been consumed, print consumer done. So then the part 1 of this, after you've created those, is I want you to create 2 threads, one for the producer, one for the consumer, waits for both of them to complete. Again, you'll do that with join, so thread1.join, thread2.join, and then prints done. So when you run this, you should have the producer produces 100 values, consumer consumes 100 values. They both print producer done, consumer done, and then we'll have done printed out at the end for the entire program. So I want you to execute that program several times and observe the output. And I want you to see, did it perfectly synchronize those? And it shouldn't, because they're delaying for different amounts of time here. So you should see, like, maybe you'll see like 1, 1, 1, 1, 1, and then on the consumer side, it will consume 1, 1, 1, 1, 1. And then maybe it'll then consume like 10, and then it might be 20, and then like 22. And then at the end, it might get to the end and consume like 100, 100, 100, 100, whatever. But I want you to run that and see how well it does at staying synchronized and how many numbers get missed. So in other words, we might have numbers that are duplicated, like 1, 1, 1, 1, 1. We might have ones where it skips over numbers, like it jumps from 2 to 12 or 5 to 7 or whatever, where it skips some. Then I want you to comment out the sleep lines here and here and run at full speed. And then I want you to see what it does. So I want you to describe to me how that changed the output. And then after that, then I want this is going to illustrate that there are problems with that producer consumer, because right now, as completely separate threads sharing that buffer variable between them, one writing to it, the other reading from it, with no synchronization, we're going to have some of the values get missed. We're going to have other ones get duplicated. So this is going to create a problem for us. So we need to fix that. And we're going to fix that with semaphores. So I want you to add the sleep instructions back in. And then I want you to add semaphores to the program so that the shared variable for both the read and write are protected. And there are a couple things that I want you to consider here. You need one semaphore to make sure you're not producing and writing over the top of something that's already there. And then I want you to write another, or you're probably going to need another semaphore that makes sure that we're not consuming from a thread from a producer that hasn't yet produced. So you're going to have to, it's like, think of one semaphore saying, this one blocks when the buffer's full, another semaphore blocks when the buffer's empty. So you're probably going to need a couple of semaphores to do this correctly. And I want you to execute that several times, make sure that it works correctly. And what you should see on your output is 1, 2, 3, 4, 5, all the way to 100. The producer stops, consumer, or producer done, consumer done, whole thing done. And if you run that multiple times, you see the same output every time when you run that. So go and answer, did each run produce the same results? Were all 100 values now displayed properly? And how did that change our output? Did it work right? And so we're adding this kind of conditional synchronization that we don't want to produce if something hasn't been consumed. We don't want to consume if something hasn't been produced. And you're going to use semaphores for that. And you might think about what since there are going to be 2 semaphores, they're going to have to think about what the starting value of each of those would be. Okay, so that's the lab. Let me go back to the presentation. So back to the presentation. That's all we're doing today. That's all we're going to cover today. But I want you to spend the rest of the time. This is a relatively short lecture. And I want to give you time, in-class time, to work on that. So I would suggest that you actually use the time that you would have in class to actually work on this and get those labs done, because you only have a week to work on that. So finish up lab 2, which is going to be due shortly, and work on lab 3. And really, if you work on that today, there's not a lot of code you have to write. You should be able to get all of that done today and submitted today. So take advantage of this in-class time to work on that. And if you get stuck and you have questions, shoot me an email, send me a text message, give me a phone call, get a hold of me. I'm more than happy to help. If we need to set up a Zoom call, I can get on there and we can have a little video conference so you can show me what you're working on, share your screen, and we can look at it, and so forth. But use the class time to work on that. You shouldn't have an excuse that, oh, I had too much homework and I didn't have time, because I'm giving you class time today to work on this assignment, finish the previous one, work on this one, and neither of those are a lot of code. And if you start to get behind on this stuff, it's going to snowball, so keep up with it. And again, if you have questions or you get stuck, send me a message. I'm happy to help. All right, that's all for today. Stay safe, wear a mask, wash your hands. If you're out and about around other people, social distance if they're not part of your household, and do your part to keep yourself safe and keep other people in the community safe. And I'll see you guys next time. Let me know if you have questions.